Alright, let's work on the next problem. So, first problem of the day is going to be LeetCode number 19. Remove nth node from the end of the list. Given the head of a linked list, remove the nth node from the end of the list and return its head. Okay. I feel like this used to be an easy problem. Though, going back to some of the easier problems in my own time, it seems like some of them have been bumped up to medium level. I'm guessing that just has to do with LeetCode automatically tuning their problems. Whenever a problem hits above or below a certain submission acceptance threshold. But in any case, so this seems like a 2 pointers like problem. Where something like a 2 pointers approach would work. So let's see, let me map this out. So first we'll have probably 3 pointers actually. We'll have a slower pointer. We'll have our actual pointer. I know that some of these names don't make much sense right now, but I'll explain them in a little bit. And then we'll have a fast pointer. So I guess I'll call this a slow pointer. So the fast pointer will, let's see, should be n steps ahead of actual pointer. So what I mean by that is that if we have, so if n is equal to 2, then we should have actual.next.next is equal to fast. Something like that, right? So the idea is that once the fast pointer hits the end of the list, then we know that our actual pointer is at the node that we actually want to remove. Our actual pointer will be moving at normal speed and represents, like I said before, the node that we actually want to remove. So pretty standard stuff. And then our slow pointer is mainly there so that removing the node is actually possible. And what I mean by that is, in order to remove the node, we take the previous node and then we set the previous nodes next to the current nodes next. And then that way we sort of disconnect our actual node from the linked list. This should run in O of n time. Since we're not really incrementing through this in a way that really scales that much with our input size. We're mostly just moving pointers around a little bit. I think you can argue maybe like if we have a fast pointer and an actual pointer that that moves like the difference is large, then we might iterate essentially over the list twice. But I don't think it's I don't think it really scales much beyond that. And of course, this is also constant space, because all we really need are the 3 pointers, right? We only need those 3 pointers in order to delete the node from our list. So I think this is a pretty fair assumption of a solution that will probably work. So let's go ahead and code it up. So we'll start with our fast pointer, and we'll start this at head, and we'll say if head is null, just return actual slow, and then we can say for I in 0 to n minus 1, if fast question mark dot next is not null, fast is equal to fast dot next. Are we guaranteed The number of nodes in this list is sz, or size. We'll just call it n, but I guess n isn't used because n is also within the parameters of the function. And we're guaranteed that n is within the size constraint. Okay, so in that case, we can say here, fast is either at some node in the middle of our list or at the end of our list because of the constraints of the problem. So there's no way that node can be null in this case. So let's see. If fast.next is null in this case, so if we're at the end, we just need to move the head up. So in that case, what we will do is that we will just return head.next. And we don't really need to do much beyond that. Otherwise, if fast next is not null, that's when we start moving our nodes around, right? These should be variables, not values. And this should be a nullable. And this will start off as null. And I'm sure that these will also be inferred, so. But this nullable, if we're setting it to null, if we're initializing it as null, then we need to set its type. Okay, in this case, we'll say while fast next is not null, we'll say slow is equal to actual. Is actual a keyword? Because it's highlighted in blue. Interesting. We might have to change that name if it's actually a keyword. We'll say fast is equal to fast dot question mark dot next. Slow or actual is equal to actual question mark dot next. So now move until fast is at the end of the list. And then we can say slowed. So now, let's see. Let's see. We actually want this to be n-2, right? Or actually, we could do 1 to n-1. Because the idea is that the first node from the end of the list will be at 0. And since fast starts at head, then we want it to go to the end if it does. So in this case, head. And if this is 2, so it'll move 1, 2. And then actual will be here. So here, 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 here. That's move 1. That's move 2. But realistically, we wanted to move less. We'll come back to this in a little bit. I just want to flesh out the logic of the other parts first. Okay, so now we're at the end of the list. What do we want to do? We want to set We want to set our slows next to our fast. No, we want to move our slows next to our actual next. And then we set our actual next to null. And then that's all we need to do. And then we return head. The idea here is that we just need to move the slow pointers next to the actuals next. And then we're done at that point. Okay, let's go back to this. Let's go back to this and think about this some more. So when we start everything here at the head, let's say we move, so n is equal to 2. So this is 1. This is 2. And actual still remains here. So when we move here, fast moves here. When we move here, fast moves here. Interesting. So it seems to me that perhaps we want to move until fast is we want to move until fast is null until we go 1 off. So rather than fast next is null, we want to move until fast is null. Let me think. We could also consider the fact that in this case, our slow node isn't necessary because we are always 1 node slower. Which might actually be the play here. Because then we can reduce our complexity by 1 more. So now it's fine because our actual pointer is the should be n plus 1 steps ahead of actual pointer. The node before the 1. So now we don't need this. Actual next is equal to actual next next. So this sort of compresses it back to a standard sort of 2 pointers approach. So now it's fine that our pointer is a little bit slow. So here we have 1, 2. So 3 is where fast is. Actual is at 1. Then we go 2. You go to 4. You go to 3. You go to 5. And we want to remove the next node. So what we'll do is that we'll set 3's next to, or this 3's next to 3's next, which happens to be 5 in this case. And then we'll set the next value of the next pointer to null. Though this is actually not necessary. We could just remove that. It's probably for the best to drop references when they're not needed. But we could also imagine that this may be something either garbage collected in a language like Java or Kotlin, or in the case of if we're doing something that has more memory management like C++, when we actually delete that pointer, this would be something that would be considered within the destructor, right? So within the destructor, we would say something like if the next pointer is not a null pointer, then we want to drop that reference, right? In order to clean things up. But I think in this case, it's perfectly fine to just leave it as is. Cool. Let's see. So it's fine that it's moving a little bit faster. That's fine. Let's see for this one. In this case, we have fast and actual starting at head, both. For 1 until... This starts at 1 until 0, so this doesn't move. And now fast next is null. So we just return head next, which is null. And we get that. That's fine. Head is here. Fast is here. Fast does not move because n is equal to 1. So 1 minus 1 is 0. So from 1 to 0, since 1 is greater than 0, then it doesn't move. Fast next is not null. But and fast next is not null, so now we move. In this case, this would not work because the fast and the actual are on the same pace. Right? Because here it doesn't move. Let's see. So maybe we want this to be 0 to n minus 1. But then now we have to account for this. So when this is 2, so this will go 0, 1, 2. So slow is, or the actual is here and the fast is here. So then we want to drive it until it's null. Here, well, it doesn't do anything because the next is null, so it doesn't really move anything. Here, let's see. Here, we move 1. Fast, the next is null, so we just return head next. Which actually is also not what we want. If we do this, then you go to here. You run to there. Because the idea is that we do want to remove this item from our list. So we're at the head and we're at the tail. Let's think. So it's either because we want to remove the last item from the end of our list. If we wanted to remove our last item from the list, we don't actually return head next. What do we actually return? If we wanted to move... This problem is turning out to be a little bit weirder than I expected. What if we moved our actual at the same time? If we moved our item all the way to the end... Well, it wouldn't move all the way to the end. If we wanted to remove the last item, then this will fire, right? Okay, yeah. Okay. So I guess what we want to do, return the head if are at the end of the list fast next is null. When do we want to return head? Well, actually, I don't think we need to really account, or we don't need to add an additional case for that. Let's see. So while head next is not null, then we do this, and then we just set it to next. So in this case, so we have 1, 2, here, then you go to there, you go to there, 3 sets next to 4's next, which is 5. Okay. Here, it wants to move once, but its next is null, so we don't. Then, in this case, next is null. So the next, so we set the heads next, or the actual next, to the next, which is just null and also null. But the heads next is already there. So this example breaks. Let me think about this. And then for this one, we move once. No, we don't move once. We don't move once because this is 1 to n minus 1. Okay. So both of them stay ahead. Then while fast next is not null, we move you to next. It seems like it would be useful to have a slow pointer. It seems valuable to have a slow pointer here. Let me use... We could also just manually carve out a provision for it. Yeah, slow pointer it is. So type list node question mark null. Slow is actual. Slow.next is equal to actual.next. So this starts off as null. So now when we go 0, 1, 2, slow is here, actual is here, then actual goes here, slow goes here, and actual here, or fast here. Then when fast is here, actual is here, slow is here. So we kind of need to actually go one more. Or in this case, we could start fast at head next. And I think that would solve most of our problems. So now if head starts here, actual here, and then let's see, 1, 2, 3, and then you go 1, 2, 3. So actual will be here, slow will be here, and we set slow next, actual next. And that's fine. In this case, fast starts at head next. Slow is still null. So null, we set null to null, which doesn't really do much. And then we can say if slow is null, that means that slow hasn't had the chance to actually do anything. So in that case, then we just set to head next. Otherwise, then we can just return the head. So the idea is that if the slow value hasn't actually changed to anything that is non-null, then we haven't actually moved our slow pointer beyond the head, and therefore we should just return the next value within head. Similarly for this one, but this one kind of breaks it, right? Because now fast next is null, so we don't want to move it after here. Let's see. Because the fast is null. The fast next is null. So we're at the end of the list. If fast hasn't moved. So let's see. We have, I think, 2 scenarios. Fast is equal to actual. Slow is null. That means that we haven't moved any amount. Then we also have fast is equal to end of list. Slow is null. That means we want to remove the last element within the list. So we haven't moved any amount, then return head next, I think, is the correct option. If we haven't moved any amount, then what does that mean? if we haven't moved any amount, we are either at the end of the list or there is only one element within our list. If our fast is at the end of the list but our slow is still null, then that means that we have a 2-item list with the removal of if n is equal to 1, then do slow or actual next is equal to null. If n is equal to 2, return head next. If we are at the end of the list and our slow is still null, right? Because if n is equal to 2, then it won't move at all anyways because the head's next is null. So if our slow is still null at this time, then we kind of know that it's a 2-item list. If the head is still null, yeah. What about a 3-item list? Like if I had 1, 2, 3, n is equal to 2, then fast would start here and it'd go 1. And that's fine because 2 minus 1 is 1, so it only moves 1 item. Then actual is here, slow is also here. And we want to remove the second from last. Well, slow is null. N is 2. So we return head next, which is incorrect. Okay. There's got to be a more elegant way to handle this. Let me think about this some more. N will be less than or equal to size. We did 0 to n minus 1. If the value was, so this goes 0, 1, or, yeah. Because it's 0 here, because it's 1 here, and because, okay, so it stay here. And the actual stays here. You can have like a number of, or index plus plus, and we can say if index is equal to n, well, it should be equal to n in all cases, Mm. Well, not necessarily. Let's see. Yeah, that's fine. And fast next is null. Fast is at the end of our list and traversed its entire length. Let's see. For example, here. One, two. Right, this jump because 0, this jump because 1. Or this jump, you jump from here to here because it's 0. You jump from here to here because it's 1. And now you're at the end. You can't jump again because, well, that's the limit. But now you're at the end. You're at the beginning. Well, the number of jumps was 1 and 2. Let's see, if index is equal to n, else if index is greater than n, or sorry, less than n. So we wanted to jump more than we could. Like for example, if n, well, n can't be more than the size of the list, the number of nodes, right? Right, but if we wanted to jump 3 times, which is the number of nodes, right? So we wanted to jump 1, 2. If we wanted to jump a 3rd time, because the size of n is 3. So this jumps because 0, this jumps because 1. We can't jump again. If this was 3 though, then index would be less than n. Then we return head next. Otherwise we return, or we want to do actual head next is head next next and return head. So this, we wanted to jump more than we could. Basically, we want to remove the head element. We jumped as much as we wanted. Therefore, remove the next element from our list. For example, if this was So we start here. We go 0, then 1. Actual is here. So actual's next is not null, so this won't get triggered. Here though, we start at head. We want to go, we jump once. Head next is null. And index is equal to 1. So we set our head next, our ones next to null, and then we return 1, which works. Here we want to jump, but we can't, right? Because the next is already null. But then we're at the tail. So index is less than n because we wanted to jump once, but we could only jump, or we couldn't jump anytime. So we'd return head next. So I think this works. So then we don't actually have to care about this at the end. So then we can just focus on setting the slow, in this case, to an actual reasonable value, where slow will always have a value at this point. Because if this is incorrect, if fast next is not null, then that means that we still have a value to increment. And therefore slow will have a value. And I think this can just be here now, because slow should never be null after this check. If slow is null after this check, then we have done something critically wrong. So let's go ahead and run the code and let's see where we're at. Oh. If head is null, we just return null. Though our size is limited to 1, so this technically won't really do anything. Let's see. This starts at head. This goes to 1. This jumps because it's 1, or 0. This jumps because it's 1. Then actual is here, slow, or actual is here. Then here. And slow is there. I see. Is there a point to having a slow node then in that case? I feel like I'm flipping back and forth on this, but actual next is equal to actual next. And then these bottom two cases should be handled by this case right here. So basically the general idea is just that we don't want the fast and actual pointers to be the same. Because if the actual and the slow pointer, or if the actual and the fast pointer are the same, then we run into an issue. So the only cases in which the actual and the slow, or the actual and the fast pointer will be the same is if there's not enough room for the fast pointer to jump, in which case that's handled here, or if the in the case that the actual is already at the end of the list, or the fast is already at the end of the list, and then we can just remove the element from here. So actually, I think we can simplify this logic a little bit and say index is less than n. We can remove that comment. I don't think that's particularly helpful. So now this should still run the same, but this actual next is equal to this leapfrogging at the end is actually helpful. So we just want to avoid having our actual and our fast be the same, because then we can't actually swap the pointers. Let's go ahead and throw a submit, and let's see if there's any other additional cases that we haven't accounted for. Okay. This one was a little bit tricky. Not gonna lie, it was a little more complicated than I expected originally. But ultimately, like, there weren't that many cases to think about. I think I just got tripped up really in sort of trying to make everything work, and like I was trying to think about the solution rather than thinking about the problem that we needed to solve. And I think that's what ultimately caused me to take so long on this problem. Or at least more time than I really needed. But in any case, so it's a 2-pointers problem. And you don't need a slope pointer, but you do need something to track to see if you jumped as many times as you wanted. Otherwise, essentially, you want to remove the head pointer. In any case, I hope you learned something, and I'll see you for the next problem.